We'll explore how they describe motion in a plane and learn to analyze key characteristics related to direction and rate of change. Our main objective is to help you identify key characteristics of parametric motion. By the end of this video, you'll be able to tell which way an object is moving, up, down, left, or right, just by looking at its parametric equations. So, what are parametric functions? Think about describing the path of a particle moving in a plane. To do this, we need to know its x-coordinate and its y-coordinate at any given time, t. Instead of a single equation, like y equals f of x, we use two separate equations, x equals x of t and y equals y of t. The variable t is our parameter, and it represents time. As the value of t changes, the values of x and y change accordingly, tracing out a path in the xy plane. A key concept here is direction. As time t increases, the particle moves along the curve in a specific direction. We can visualize this by imagining arrows on the curve. This direction of motion is a crucial feature that standard y equals fx equations can't describe. Parametric equations bring motion and time into play. Now, let's explore our first key concept, analyzing the direction of motion. How do we determine if the particle is moving to the right, left, up, or down? The beauty of parametric equations is that we can analyze the x and y components of motion completely independently. This makes the analysis much simpler. Let's start with horizontal motion. We look at the x component, x of t. If the x-coordinate, x of t, is increasing as t increases, it means the particle is moving to the right. It's getting further to the right on the x-axis. Conversely, if the x-coordinate, x of t, is decreasing as t increases, it means the particle is moving to the left. The same logic applies to vertical motion. We look at the y component, y of t. If the y-coordinate, y of t, is increasing as t increases, the particle is moving up. And if the y-coordinate, y of t, is decreasing as t increases, the particle is moving down. It's getting lower in the plane. So, to recap, increasing x means right, decreasing x means left, increasing y means up, and decreasing y means down. Let's see an example. Let's analyze the direction of motion for a particle whose path is given by these parametric equations. Our equations are x equals t squared minus t and y equals 2t plus 1. We'll analyze these on the time interval from t equals minus 2 to t equals 2. First, let's analyze the x component, x of t equals t squared minus t. To see if it's increasing or decreasing, let's pick some test points within our interval. We can calculate x at t equals minus 2, 0, and 2. At minus 2, x is 6. At 0, x is 0. At 2, x is 2. Let's animate this on a number line. As t goes from minus 2 to 0, x goes from 6 to 0. Since the x value is decreasing, the particle is moving to the left during this time interval. Notice the arrow pointing left. Next, as t goes from 0 to 2, x goes from 0 to 2. Since the x value is increasing, the particle is moving to the right. See how the arrow now points right? Now let's do the same for the y component. Y of t equals 2t plus 1. At t equals minus 2, y is minus 3. At t equals 0, y is 1. At t equals 2, y is 5. Let's animate this on a y-axis. As t goes from minus 2 to 2, y continuously goes from minus 3 to 5. Since the y value is always increasing, the particle is always moving up during the entire interval. So, we can combine these findings. From t equals sign 2 to t equals sign 0, the particle is moving left and up. From t equals sign 0 to t equals sign 2, it's moving right and up. Here's what the full path looks like. Notice how the direction changes. For t less than 0, the path goes up and left. For t greater than 0, the path goes up and right. The change in direction happens at t equals 0, where x changes from decreasing to increasing. This brings us to a critical second point. The direction of motion can be different at the same geometric location in the plane. This might seem strange at first. You can be at the exact same coordinates, say 1, 2, but moving in a completely different direction depending on the value of the parameter t that gets you there. The reason is simple. A standard function, y equals f of x, has to pass the vertical line test. You can't have multiple y values for a single x value. But a parametric curve can cross or retrace its own path. A particle could pass through the same point in space, multiple times. Imagine a particle moving in a figure-8 pattern. It passes through the center point twice. At time t1, it might be moving up and to the right. A little later, at time t2, it passes through the same point again, but this time it might be moving down and to the right. This animation illustrates the point perfectly. The particle is at the same physical location twice, but it's clearly headed in different directions. This highlights the power of parametric equations. They not only tell us where something is, but also when it's there and how it's moving. A single point xy doesn't capture the whole story. The parameter t provides that context. Our third key concept is that the same curve in the plane can be parametrized in many different ways. This is a very important idea. Imagine a road in the shape of a circle. You can drive a car on it, a bicycle on it, or a snail could crawl on it. All three follow the same path, the same geometric shape, but they do it in completely different ways, with different speeds and directions. The parametric equations are the driving instructions, not the road itself. Let's look at a concrete example. All three of these sets of parametric equations describe the exact same curve, a parabola opening upwards. Let's verify. For the first set, if x equals t and y equals t squared, we can just substitute x for t and get y equals x squared. Simple. For the second set, if x equals 2s, then s equals x over 2. Substituting this into the y equation, we get y equals 4 times x over 2 dash squared, which simplifies to y equals 4 times x squared over 4, or just y equals x squared. Again, the same parabola. For the third set, if x equals negative u, then u equals negative x. Substituting, y equals negative x squared, which is also just y equals x squared. You see, all three give us the same geometric shape. However, they describe different motions on that shape. Let's compare the first two, for t and s greater than or equal to 0. In the first case, as t goes from 0 to 1, x goes from 0 to 1. In the second case, as s goes from 0 to 1, x goes from 0 to 2. The second set of equations traces out the parabola twice as fast. What about the third example, xu equals dash u? This would trace the parabola in the opposite direction, from right to left. The takeaway is this: a parametric representation captures more information than a simple function y qualify of x. The equations themselves define the curve and its behavior, speed, direction, and even retracing, all at once. Let's move on to our fourth and final key concept, the average rate of change for parametric functions. This is our bridge to the idea of a slope. Over a time interval from t1 to t2, we can compute the average rate of change for x and y independently. Think of this as their average velocity. The average rate of change of x is the change in x divided by the change in t. It tells us the average horizontal speed. The average rate of change of y is the change in y divided by the change in t. It tells us the average vertical speed. Now here's the magic. If we divide the average rate of change of y by the average rate of change of x, we get a very meaningful quantity, the slope of the secant line connecting the 2 points on the curve. These points correspond to the times t1 and t2. The delta t terms cancel out, leaving us with delta y over delta x. This is exactly the familiar slope formula. It's the ratio of the total vertical displacement to the total horizontal displacement over that time interval. Visually, it's the slope of the straight line segment that connects the starting point, x, t1, y, t1, to the ending point, x, t2, y, t2. It's crucial to note that this formula works as long as the average rate of change of x is not 0. If it were 0, it would mean there was no horizontal displacement, resulting in a vertical line whose slope is undefined. Let's work through an example of finding the slope of the secant line for our previous parametric curve. We have x equals t squared minus t and y equals 2t plus 1. Let's find the slope of the secant line between t1 equals minus 1 and t2 equals 2. First, let's find the coordinates of the 2 points at these times. At t equals negative 1, x is 2 and y is negative 1. At t equals 2, x is 2 and y is 5. Next, let's find the average rates of change for x and y. The average rate of change of x is the change in x divided by the change in t, which is 0. The average rate of change of y is the change in y divided by the change in t, which is 2. Now we find the slope by taking their ratio. The slope of the secant line is the average rate of change of y divided by the average rate of change of x. Since we have a 0 in the denominator, the slope is undefined. Let's look at the graph to see what this means. Notice that the secant line connecting the 2 points, 2, -1, and 2, 5, is a vertical line. This visually confirms our result. The slope is indeed undefined. This example reinforces why we need to be careful when the horizontal displacement is 0. But it also demonstrates how these concepts of rate of change lead directly to the geometric concept of slope. Let's quickly recap what we've learned today. First, we learned how to analyze the direction of motion by looking at the x and y components independently. Increasing x means right, decreasing x means left, increasing y means up, and decreasing y means down. Second, we saw that the direction can change at a single point if the curve crosses itself. The parameter t provides the crucial context of time and direction. Third, we established that there are many ways to parametrize the same curve, leading to different motions on that path. And finally, we connected the average rates of change for x and y to the slope of the secant line connecting 2 points on the curve. You are now equipped with the essential knowledge to identify key characteristics of parametric planar motion. Keep practicing, and you'll become an expert in describing motion with these powerful tools.